Hi guys, it's AD, your favourite armoured penguin again. My apologies for the quiet time. I actually had my microphone, my brand new microphone, packed up, so I've had to make do. So my apologies if this sounds at all noisy or quiet. I'll do my best to try and make up for that. Now this is to do with my video, Jeran doesn't understand the speed of light. Some of the comments on that video, explaining how Jeran has completely misunderstood how rigid objects, movement and the speed of light actually affect the world, want me to just expand on the explanation that I give in the video. So I want to point out that I'm not a material scientist, I'm not a physicist beyond my own studies, my A-levels. Although I am doing astrophysics on the Open University at the moment, I haven't got very far in it. So if you are a physicist and you want to address anything here, please, I'm more than happy to make any corrections here. This is based on lectures that I had decades ago. My memory is not the best. I have done rudimentary research, and as far as I can tell, all the physics websites actually agree with what my recollection is. So the particular comment on YouTube is:
Young's modulus is meaningful only in the range in which the stress is proportional to the strain, and the material returns to its original dimensions when the external force is removed.
Now, for the purposes of Jeran's thought experiment, this doesn't really come into it. Because he's dealing with sticks and ropes, and basically in the real world, you're dealing with objects that would collapse under their own weight. If you're dealing with a stick or a rope that's 433 light years long, it would actually collapse into a black hole. That's what sort of stress we're talking. So what we're going to do for the purposes of this, as it is purely a thought experiment, we're going to ignore gravity, and we're going to assume that the only two forces on those are at the either end of the rope or the iron bar. I'm actually going to replace everything in here with an iron bar because it makes things a lot simpler. So the comment goes on:
So if I was pulling on the bar or a machine while readjusting my grip every few seconds at no certain interval, but only with enough force to move it but not visibly stress it.
So this is why I'm taking out those extra forces, because now we can just concentrate on what happens at either end of that bar. And the thing is that the movement of the object is applying stress, so there would be no possible way to do this without simplifying this down to that level. There is no object that is perfectly rigid. There are hypotheses that in the centre of black holes you could find perfectly rigid material, but unfortunately to verify that you would have to go to the centre of a black hole, and if you could do that, gravitational time dilation suggests that you'll never actually get there anyway. So one of the reasons that objects are not rigid is because basically a solid object is mostly empty space. Atoms are made from a tiny nucleus and then spaced, well, in relative terms anyway, a long way from it is what we call the electron shell. But the majority of the single atom is the space between that nucleus and that electron shell. And what this means is that even hard solid objects have a certain amount of bounce to them, or deformation to them. Obviously diamonds have less bounce than rubber, and given that the electron shell is what gets interacted with, and the mass or the inertia of the atom is actually in the nucleus, we can look at atoms as a suspension system. So your electron shell can be formed around the nucleus, but your nucleus is effectively what gives the atom mass.
Why would it take 433 light years for the other person to notice after I've lightly pulled a number of miles worth?
Now this is ultimately because of inertia, which is a product of mass. And the best way for me to explain this is it works for myself anyway, and hopefully the analogy works for you guys too. When you drive a car onto a ramp, the front suspension deforms, but the car keeps going in a straight line, at least for a little while. And this is because the car has all the inertia, And while your wheel is moving upwards, it takes a while for that upwards movement to be transferred to the weight, the actual mass, the vast mass of the vehicle. And in the same way, electron shells of atoms are actually elastic to the nucleus. You can deform them, and they will return back to their original shape, but they won't. The actual atom itself, the actual mass, won't move until the nucleus has moved. And elasticity has a big effect on the problem here. Ultimately, any kind of compression wave is the elasticity of the medium impacted by the inertia of the object, or the inertia of the atoms. Effectively, elasticity is effectively elasticity over the density, so divided by the density. And this is how we work out the speed of sound, which are compression waves, which is exactly what we're looking at, through solid objects. It also works for liquids as well. And this means that even though stone has a lower density than most metals, there is less inertia to be moved, basically. Your movement will be transmitted quicker through the metals because they have a higher elasticity. But what is elasticity, and why does it have such an effect? Well, elasticity is basically the speed at which an object, once deformed, will return back to its original shape. And this is where Young's modulus comes into it. So, I guess a simple way to look at this is if we go back to the car suspension analogy, then a higher elasticity will behave more like a sports car. So where a sports car will, after you've taken a corner or driven over a bump, the suspension will go back to its original shape. It will snap back to its original shape as quickly as possible. Whereas if you're looking at something with a lower elasticity, you're thinking more something like a 4x4, for example. And the 4x4 will take a lot longer to return back to its original shape. So if our 433 light-year bar is made of iron, let's just keep it simple, it's made of iron, then the speed of the wave, or the shove, or whatever you want to put through it, the pull, actually travels through that bar at a speed of 5.1 kilometers a second. So what we've done there is we've taken the elasticity of iron and divided it by its density, and that's what gives us the 5.1 kilometers a second. And given that the distance is 433 light years, now there are two ways that we can work this out, and I'll do them very roughly so that you can follow it through. Now, first off, 1 light year in meters is roughly 9.5 million billion meters, making 433 light years about 4.1 billion meters. So that means at 5.1 thousand meters a second, it takes approximately 801,000 billion seconds, or if we break that down into years, that's 25.4 million years to make the trip. So alternatively, and this is just a way so we can check our numbers are correct. Okay, we can divide the speed of light, which is 300 million meters per second, roughly, divide it by 5.1 kilometers a second, and then we get the ratio of the two speeds. And if we take that and multiply it by 433 light years, then we can see how long in years it would take to cross that distance. And giving the rounding errors in both of our methods here, for instance, 1 light year in meters is actually 9.4, it's not 9.5. And I've rounded up the speed of light to 300 million meters per second, which it isn't, it's a little bit less. We get a different but very, very close number of 25.3 million years. So instead of 25.4, it's 25.3.
I'm not a physics PhD, I'm just learning. If you're too busy, then I understand. We all have stuff to do.
Now, not at all. I'm also not a physics PhD, and in fact my tertiary education stopped at A-levels until I joined the Open University. And I've got some industry-specific software qualifications, but apart from that, I'm not a particularly educated person either. But the whole reason for me starting this channel was so that I can learn, and I can share what I learn with others. I am eternally curious, and I pride myself on trying to understand things, even when they go against my beliefs or common sense. For me, it's very important that I don't do what Jeran did here, and I use this last section of the video to clarify what I mean by that. You see, Jeran's whole position on this is, well, I cannot understand how this can be true, therefore it cannot be true. And this is so unbelievably close-minded that it goes against everything that my dad actually taught me. This world is a wonderfully complicated place, and the farther we reach into our understanding of the universe, the harder it becomes to understand anything. And the more specialized science becomes, the harder it is to understand everything. You see, the scientific community is making things harder as well by hiding everything behind paywalls and monetizing knowledge. And this actually plays into Jeran's fear of being talked down to, just because he doesn't understand. But Jeran is an idiot. He's not an idiot because he doesn't understand. He's an idiot for deciding that because he doesn't understand, there's no way that he can be wrong. Now, you see, I was hoping that when he had his conversation with Aaron Ra, that it would have left a bigger impression on him, or even his failure when it came to behind the curve. One of Jeran's biggest failings is that while he makes the claim that all men lie, he doesn't see how he falls under this statement. And Jeran lies continuously. Anything that he doesn't like or doesn't understand is written off regardless of the evidence for it. But worse than that, he will posit that what he says is just my thoughts, or I'm just asking questions. And that is my biggest problem with Jeran. So I hope everybody was able to follow this, and if you are more knowledgeable on this subject than I am, and you can spot any problems that I've made, please let me know, and either I will change this, I will release a correction, or if you're up for it, we could do one together. Thanks, guys. I really appreciate you watching this and listening to what I've got to say, and hopefully the next one won't be so long. Cheers.